All right, everyone. Welcome to the first part of our course on the theory of limits. To begin with, let's define our function f of x to be x squared minus 1 over x minus 1. And then let's find the value of this function when x goes to 2. So that would be f of 2 to be, this is be 2 squared is 4 minus 1 over 2 minus 1. So that would be a 3. So as x goes to 2, f of 2 is 3. Now let's see the case whereby x equals to 1. Then f of x would be 1 minus 1 all divided by 1 minus 1. So this will be a form of 0 all divided by 0. Now, this is indeterminate. So this is the first indeterminate form we are going to evaluate. This is the first, I'll write it out. So the form of 0 to the power of 0. So the first indeterminate form we are going to evaluate. Now, the reason why this is indeterminate is that we don't really know, okay, I meant to write 0 divided by 0, actually. So form of 0 divided by 0. So here, we don't really know. Division by 0 is not defined. That is what I mean. We can't divide numbers by 0. So what you do in this case here now is that f of x being given as x squared minus 1 over x minus 1. So we ask ourselves, since we can't actually find the value of x when x is 1, what about when x is close to 1? When x is close to 1, what do we do? So this is what we are going to focus our mind on. The value when x is 1 cannot be found completely. So we are going to ask ourselves, what happens when x gets close to 1? Well, when x gets close to 1, what happens? Since we're no longer interested in what happens when x is 1, yeah, this is what we can do for f of x being equals to x squared minus 1 over x minus 1. We can say this is equals to x minus 1 multiplied by x plus 1. And then this is x minus 1. Now, we can cancel out the ones out. Now, you may ask me, why do I cancel out the 1? Because are we not dividing by 0? Actually, we're not dividing by 0 because this case here, x is not 1. X is never 1 to begin with. We are only asking, okay, this expression f of x now, how does it behave around 1? Like, let's say this is the interval on the number line, and this is 0, and this is -1, and this is 1 there. So how does x behave when it gets to 1 through this point or through this point? But we don't really care what happens when x is 1. We don't really care about this position. We want to know how does f of x behave around 1. So we have the right to cancel out x minus 1 out of our equation because x is never 1. So this will become x plus 1. Like f of x will become x plus 1. So we know that if x gets close to 1, f of x as x tends to 1, that is what we know. F of x will definitely go close to 2. In this case, we write that the limit as x approaches 1 of f of x is equals to 2. Now, we don't really say that f of x is 2 when x equals to 1. It's not the case. What we are saying is that around 1, f of x behave like 2. So f of x approaches 2. And that is the concept of limit and how it is defined. When we say the limit of an expression as x tends to a of f of x, we mean that f of x, if we define this to be L, what this means is that f of x approaches L as x approaches a. Now, what does it mean for f of x to approach L? What it means that f of x, let me close a division here. Okay. What we mean is that f of x minus L, f of x minus L is small, is very small. Like f of x minus L, the absolute value of f of x minus L, or this whole f of x minus L, is actually close to 0. Let's say f of x minus L is less than epsilon. When we say less than epsilon, it means that it's epsilon is a very, very small number. A very, very small number that is actually close to 0. So it means that f of x minus L is less than epsilon whenever x minus a is less than delta. we can actually pick another delta out, because in this case, both delta and epsilon represent numbers that are very, very small. They don't actually mean much. Most people think that epsilon is another strange number and delta is another strange number. It's not the case. The case for epsilon and delta is that they represent a number that is very, very small, like infinitely small. That means that f of x gets close to L whenever x gets close to A. So let's see, or let's over to the next board. Now, in the previous board, we discussed that the limit of f of x, which is defined as x squared minus 1 over x minus 1, as x approaches 1, f of x approaches 2. This means that the f of x minus 2 is less than epsilon. Let's say f of x minus 2 is less than delta or epsilon. Let's say less than epsilon. Whenever x minus 1 is less than delta. Now, this is the epsilon delta definition of limit. And this says that I won't define it because I'm not here for the formality of it. What I mean is that for the concept of limit, we're not interested in what happens when x actually equals A. But what happens when x is very close to A? That's when x minus A is very, very small, less than epsilon or less than delta. What happens when x minus A is very, very small, less than delta? Then and this means that if that limit is L, that means the function f of x minus that L is very small, like very small. Now, in the previous board here over, you can observe that as x gets close to 1, this function actually gets close to 2. So the difference between this function and 2 is very, very small. And that is the concept of limits. Thank you for tuning in, and please do subscribe to the channel. Thank you.